Example 4 is just one of those problems that really just tries to put exponentials into context. Like, it tries to put what we're doing in examples 1 and 3 actually into a real scenario. And I'm not sure exactly how accurate this is, but I mean, it seems accurate enough. It's something that we can kind of relate to, unfortunately. I mean, it's talking about forest fires, but I don't know. I mean, I guess it could be real. I mean, it's definitely real math, but I don't know. I mean, what the heck? It's one of those problems modeling. It's always interesting. Some people find it interesting. All right, so we're going to use an exponential model. And really most of the work is done for us, but again, let's give this a chance. So the diagram shows how a forest fire grows over time. This is actually pretty interesting, I guess. All right. Let's see. So as it grows over time, so it kind of starts in an isolated section, and then I guess it also grows out this way, but also up, and kind of also, I don't know, it kind of grows out in these like L-shaped patterns, because I guess as it grows out, and it also grows up. So, all right, I could buy it. I buy it. It kind of spreads where it can see the next grouping of trees. All right, so anyways, the fire department can contain a 160-acre fire without needing additional resources. Okay. About how many minutes does it take for the fire to become too big for the department to contain it without additional resources? All right, so granted, we're saying how long does it take to get to be 160 acres, because that's when they need more resources. All right, so it says because the ratio of the number of acres from the diagram are all 1.8. So apparently 4 to get to 7.2 times by 1.8, from 7.2 to 12.96, and from 12.96 to 23.3, apparently your growth factor is 1.8. So then each time it's growing by 1.8, so we're going to put it in the model of y equals the starting value, which I guess is 4 acres, right, at 0 minutes, 4 times 1.8 to the t, because then it's growing exponentially at every minute thereafter. Okay, so if we want to find out after how many minutes does it take to get to be 160, apparently our model is, well, when y equals 4 times 1.8 to the t, well, when are we going to get to be 160? So we'll plug in 160 for the amount of acreage. Okay, so we want to solve for time, the number of minutes, until, they got to radio in and say, hey, we can only contain this thing for this many minutes, and then we're going to need backup. All right, so like anything else, our variable is in the exponent spot. We need to get that exponent down onto the ground level, that variable down into something we can work with. So honestly, I think the first step, like anything, is to just isolate the term with your variable. 1.8 is the only thing that's getting raised to the t power. So we want to isolate by just getting that alone. So we want to divide both sides by 4. So we end up with 40 equals 1.8 to the t. And now the same thing is that you need to recognize, guys, that we need to use logs. So if we introduce log on both sides, so log 40 equals log 1.8 to the t, we know that we can invoke the property of sliding our exponent to be a coefficient. So we get log 40 equals t times log 1.8. Divide both sides by log 1.8, and sure enough, we get log 40 over log 1.8 equals t. Now, this is something we can put in our calculator. Log 40, parenthesis close, divided by log 1.8. What does it want us to do? Round to the nearest minute. So we get t is 6.27. But if you're calling it on the radio, you're going to say, hey, we got 6 minutes until this gets out of control. So, I guess it makes sense. Yeah. it's going to grow, kind of spread exponentially. The fire is going to grow because as it affects more trees, those trees affect more trees. And if there's more trees, then those are going to affect more and more and more trees. So, makes sense. We'll do a little solving. Yeah, we can check it, right? We can always check that 4 times 1.8 to the 6.27. Sure enough, we get something 4 times 1.8 to the 6.27. We get 159.44. Actually, probably 45. Or if you went out another one to 2.76, sure enough, checks out 150. So for the try it, last thing for the try it, use this same formula for the try it, except you're talking about how long it takes over a different amount of acreage.